Today's lesson from section 2.2 in the textbook, Properties of Exponents. Take a look at our learning goals. We want to evaluate and simplify expressions involving exponents, be able to state the domain and range of a relation and tell whether it's a function, and write a function in function notation and evaluate it. So, let's get started with some old but useful definitions. Definition of integer exponent starts off with let a be a real number. So we're thinking of any possible number that we've used before. From there, let a be a natural number. Now if a is a natural number, we're not including 0 in the natural numbers, remember, then any real number to the power of a natural number, so a to the first, a to the second, a to the third, a to the fourth, fifth, sixth, seventh, all the way to infinity, whole numbers, we would have an expression that we can multiply it out. So we're just reviewing here that you know powers are examples of repeated multiplication. Then again, if a is non-zero, because if 0 is to the 0 power, it doesn't work. But if a is non-zero, any number to the 0 power is 1. If you have questions on that, make sure you ask during class. We can show you why. If n is a natural number now, and we take a to the power of the opposite of n, we get 1 over that power. Think of it like the reciprocal. It's the inverse of a number. So those are characteristics you've seen before in Algebra 1. We just need to review because we'll be using them quite a bit in today's lesson. Also, as a quick review, we need to talk about our powers or properties of different powers or exponent looks. So let's start with the product of powers. Yes, it's important to know names. The names sort of go with exactly what you're looking at, but more importantly is, do you understand what to do with your values, your exponents, your base numbers? So for any non-zero number, a, and any integer m and n, if you take two numbers that have the same base and you multiply them, you better be thinking of it as adding the exponents. So like bases, when you multiply, you add the exponents. Quotient of powers property you've seen again also in Algebra 1. Start off with two variables as our base. They could be numbered, they could be variables. But they need to be the same base number, and you can have different exponents. But if you are dividing like bases, the rule is to subtract the exponents. So yes, the multiplication and division are related because of products and quotients. Now, next one, power of power. In order to have a power, you got to have something to an exponent first. So if we're looking at, we have something to an exponent right here. And if we take that to another power, we now have a power of a power. And when you take 3 sets of 4, that would be an example, a to the third taken to the 4th power. I have 4 of these sets of 3. 4 sets of 3, 3 sets of 4 is definitely 12, which is a to the m times n. Power of a product. You're going to have two things multiplied to start with, and then you take that product to a power. It's telling you that everything inside has to be taken to that power. Some people like to think of it as distributing. It's really not distributing, but it is, looks like it's related. Everything inside must be taken to that power. That exponent does have power over all of this. Power of a quotient. Again, you have a division problem to start with a power on the outside. So both the numerator and denominator must get a piece of that exponent. So there's 5 more properties there that you should be familiar with from Algebra 1, and we will be going and using those in detail in our work today. So let's look at a couple more definitions here. The definition of rational exponents. Rational, remember our definition was any number that can be written as a fraction. So these are fractions. These could be decimals, whole numbers, negative, positive. Now, in this case, we're talking about we're going to eliminate or restrict a to being all positive real numbers. So it has to be positive. Now, n is non-zero. And so if we wrote a to the power of 1 over n, that's the same as saying I'm a root of that number. So what you've seen in the past, let's talk about, you have seen a square root. Most square roots get written like this. Well, if that is equivalent, we know a square root means second power to undo it. So we need to be looking at a to the 1 over 2. Those two things would be equivalent. If I had a cube root of a, then we could also write it as a to the 1/3 power. So that root is on the bottom in the denominator of this fractional exponent. Also, if m and n are integers and n cannot be 0, what if we take a root and a power is what this is saying. So, to back up, if we had a number, a, so let's just say 3, and we were taking it to the 1/2 power, and then we were going to take it to the 5th. So you have a power of a power, then you have the power of it. So you can split it up like they have here. We could go backwards as they have and say, well, this is nothing more than multiply me together, and this would be 5/2, 3 to the 5/2 power. However, you're not really good probably with powers like that in your head. You're good with squared, cubed, 4th power. So you need to think of it as what's on the bottom is the root, so you could think of as the square root of 3, and still that taken to its power. If it was something other than a square root, you'd have to see that number out front in this general area of your radical. Okay, and then you would simplify depending upon the directions, and we're going to do a little of that today. So you can use the property going both directions. All right, with that, let's look at a couple problems, and let's simplify this first one. What looks like a big multiplication problem. Write your answer with positive exponents only. So in order to simplify, we want to be able to pull this down and write our work below. So probably as we write our work, I'm going to copy the 9a squared b cubed. But I notice that this parenthesis needs to be squared. So if we can square that quickly as we write it, a -2 squared would be 4. A to the 5th squared would be a to the 10th. Multiply, 2 sets of 5. And then b to the -3rd squared would be b to the -6th. Now at this point you can still leave your negative exponents because we have more multiplication to do. So with that, when you're multiplying, rules are numbers with numbers, like variables with like variables, and we need to finish by multiplying and say 9 times 4 is 36. A to the 2nd times a to the 10th, like bases, you add the exponents, so that's a to the 12th. Another way to think of it is counting how many a's you have totally. And then the b's remaining, b to the 3rd times b to the -6th. Again, add them together would be b to the -3rd. That is a correct answer when you have directions that don't specify like ours do. So write your answer with positive exponents only. We must take that negative exponent and turn it into a positive exponent. The only way to do that is use that inverse or reciprocal rule. So we'll end up with 36 a to the 12th all over b to the 3rd. And that would be simplified. If there was any division we could do, because of like variables or numbers that went into each other, we would do that at this point. Okay, let's simplify with a quotient to start with. Starts the same way because everything in the quotient has to be considered one group, and we are taking it to the third power. We must take everything inside to the third power. So that's where we're going to start. Think of it as a negative number, like -1, taken to the third power would leave us a negative. M to the 9th taken to the third is m to the 27th. N to the third. On the bottom, 5 has to be taken to the third. 5 times 5 times 5, 125. M to the 30th. N to the 18th. And again, here's an example where you're saying, well, we're done. Not quite, because you do have like variables on top and bottom, numerator and denominator. And we don't have any negative exponents at this point, so we're still good with keeping our positive exponents, but they're not simplified. So that's where our next step is. So just looking at the m's, m to the 27th divided by m to the 30th. That would be 27 take away 30, which is m to the -3rd. Still have our negative sign out front, all of that. Still have the 125 down below. There's nothing to change either of those. Then we look at our n's. They're next. N to the 3rd divided by n to the 18th. That's a subtraction. 3 take away 18 is -15. But here's where that rule applies now. And some people got it in their mind, oh, we don't want a negative, so they just move it right away. But this would be the inverse rule. And so the inverse rule is saying that m to the -3rd has to be flipped, and so does that n to the -15. So if they're on top, the only thing left on top now would be that -1. Everything else would be down below. In the denominator, the only thing that changes is the negative sign has gone away. That's part of the inverse look. Now, there's a way where some people say when I'm comparing back here, if I look at those and say, well, there's 27 on top and 30 of them on the bottom, so I'm just going to keep them where there's more, and that would be on the bottom. That's another way to do this and keep it positive. Here you have 3 on top, 18 on the bottom. When you do your subtracting or canceling, there's going to be 15 more on the bottom, so you want to end up that way. So your final answer should be a -1 divided by 125, m to the 3rd, n to the 15th. Next, we have several that we want to evaluate the expressions. Now, I highly recommend on these you stay away from your calculator and you work your brain. We said on any problem that was an example of a to the m over n, the top number stood for the power, the bottom number stood for the root. And if you ask yourself with no calculator, what would you rather do? Would you rather make the number bigger first, or would you like to make the number smaller? If you're working in your head, hopefully your logical answer would be make it smaller. You're working with smaller numbers, easier for you to do in your head. So if you're doing anything with a fractional exponent without a calculator, think of root first, power second. So in this case, we have a cube root because of the 3 in the denominator. So we're thinking, what is the cube root of 125? Some people even like to rewrite it that way. And as they're doing that, they're thinking, okay, what is that one number that multiplies by itself to give me 125, multiply by itself 3 times to give me 125, and that would be 5. Okay, so you can rewrite it, or you can just do it in your head. Next one. Here's one where I have a numerator and denominator that are not just 1. And so we've got 8 to the 2/3. So again, think of it as I'm a root first and then a power. So if I do the root first, and think of it that way, and then that whole thing would have to be taken to a power. So that'd be another way to write it. And that's where you want to simplify. So the cube root of 8 is 2. 2 squared is 4. 4 should be our answer. And we're done. One more. Negative 64 to the 2/3. We're looking at the negative sign is not part of it because it's not in parentheses. So we're going to leave that outside, and we're going to do this part first. So 64 to the 2/3. Without rewriting it this time, what is the cube root of 64 is what you're thinking for the 3. And that's a 4. 4 squared is 16. And with the negative sign that was out in front, we should end up with a negative 16. So we'll be practicing these, a little more complicated ones, really work on those properties, and come to class with any questions you might have about those properties.